Going live now.
Okay. Good evening, everyone. I am delighted to introduce tonight's speaker. It is Dr. Jani Radebaugh, a planetary scientist at Brigham Young University. She specializes in finding analogues to other planets here on Earth in the field. These studies have been taking her to the Sahara, the Arabian and Namib, Argentine, and Iranian deserts. Lava lakes have drawn her to Ethiopia and Vanuatu in the South Pacific. She's a team member of the NASA Dragonfly mission to Titan and has been involved with the epic Cassini and Galileo missions. You've seen her on the science discovery program, How the Universe Works. So welcome, everyone, to tonight's speaker.
Thank you so much. I'm so delighted to be here. It's really kind of a nice outcome of this past year that we are getting used to being able to talk to each other without all the, I guess, burden of travel, even though I really love travel, as you'll see soon. But I think it's enabled us to communicate better with each other, and I hope some of that sticks around. So I'm really happy to be here. One day I hope to come and see you all in person. Okay, I have some slides to share. I'm just going to give this a try. I think this should work. Everybody can see this okay?
Yes.
If I do full slideshow. So hopefully you see a picture of a robot that's descending on rockets and a little rover down beneath it. Hopefully you all saw that happen over the past month. I thought they just did a fantastic job of bringing all of that to us and showing us what happened. This is a Perseverance rover that just landed on the surface of Mars. And it's such a complicated landing. Everybody's always biting their nails about whether it's going to work or not. But, you know, they dot every I and cross every T. And so they made sure that it worked. And so I guess I'm starting out in the solar system, but I'm going to come back to Earth a number of times and just show how the way I understand the solar system is by exploring our own planet Earth. I just think the video and the pictures from this landing were just so stunning. I mean, look at the clarity on this picture here off to the right. This is a picture taken from the robot that you can see in the upper left here. There's a camera aimed down onto the rover as it's about to land. It's a few meters up off the ground in this shot. And you can see the dust getting blown around as it's getting close to landing because of the rockets. It's being lowered down on that sky crane, and the minute it touches down gently, it detaches from the landing craft, and it zooms off into the distance so it doesn't impact the rover. And everything just came off flawlessly. I just am amazed that we can see all of this detail from all the way at Mars. So why did we go to this place? I think this is a very neat oblique view. This is from an orbiter, but amateur astronomer, actually, or I guess amateur planetary scientist, took the overhead images and kind of turned it and made it look oblique. So it kind of feels like we're about to land on the surface. There's really a lot of good that the amateur image analysts are able to do for us. You know, people who are on the teams don't have time to do these beautiful products and maybe don't even have the skills, and the amateurs can do that. So I want to say this is Roman Tkachenko, but I'm forgetting if that might not be the right person. I should have that written down. But here you can see the red star where the spacecraft landed. And off in the distance, can you see this kind of lobate shape out here? You can tell that it's raised. There are a couple of shadows. You can tell there's a big line running right through it. It's a channel. And the channel emptied from the rim of the crater and actually brought material from the region all around about and emptied that material into the crater. And it would not make this shape, which is a delta shape, unless the crater had been filled with water at some point. And so it's just a kind of a smoking gun that there was water and there were deposits here. And so this is a great place to go. We're trying to go somewhere where we know water existed on Mars, because these landscapes that were formed by water on Mars, similar kinds of landscapes on Earth have always led to us finding fossils. We were just talking about this before. You need to find a place where water laid down sediment, and on Earth, if that happened, you usually can find a fossil. So we're just crossing our fingers. Can there possibly be something living there, or that had lived? I think that's kind of where the mindset is right now, had lived at some point in the past on Mars. It's a very difficult place. It's got a lot of radiation onto its surface from solar wind and cosmic rays. There's no magnetic field to protect the surface against that. It's very damaging to any kind of DNA or other kind of life. And so if there's life on Mars now, we think it had to probably be burrowed underneath the surface. Also maybe where we can find liquid water. The temperature and the pressure are not correct for liquid water now on Mars. And so if the environments were right in the past, that's really kind of what we are looking for at this point. And of course, just to be clear, we have not seen life outside of planet Earth. Does it exist out in the universe? I guess it seems likely. The more things we find out about the universe, the more stars we find with planets around them. It seems like just about every star, right, has at least a planet. So, and with the great numbers that we can think of out there, it's probably got to be there, but we all have to remember we haven't seen it outside Earth yet. It also brought a little helicopter along, and I don't know if you all saw this past week. It made a couple of little leaps up into the air, and this is a really great feat because the pressure of Mars's atmosphere is about 100th that of Earth's. It's very difficult to fly in. Had to spin incredibly fast in order to bring itself up off the surface. I want to say it's like 2,500 hertz, really, really fast. And but first powered rotorcraft on another planet, so that's pretty exciting. And I think they'll try a couple of other things. Mainly this is a technology demo, but this is actual little sort of picture stitched into a video from the rover of the helicopter on the left. Speaking of helicopters, we're sending a large rotorcraft lander to the surface of Titan. And this is a mission called Dragonfly. And I'm on that mission team. I'm not on these Mars mission teams I was just talking about. This one is really exciting. And this is very serious. This is the size of a Mini Cooper. So it's, almost as tall as I am. There are 8 different sets of rotors all across the spacecraft. It's very stable. There are a lot of kind of test flights that are starting to happen. And what's going to happen is this will be a direct entry. So the spacecraft came, the heat shield just got ejected off, and Dragonfly will be released and just fire up its rotors and start flying. And it will fly across the landscape. We'll get landscape views of the surface of Titan. I haven't told you anything about Titan yet, so that's coming. But this is just a little teaser. It will land on the surface. It will actually drill into the surface and bring materials up into a mass spectrometer and study those materials carefully, tell us exactly what the materials are made of, look at the landscape with myriad different cameras at different scales, and have all kinds of space or aircraft kind of sensors on board to understand the winds and the pressure, and can pick itself up and fly to lots of different locations across the surface. So we feel like this is a whole different level than what we gained from the rovers, which was a tremendous amount. But when we can pick up and go 20, 30, 40 kilometers to the next location, that's a whole different level. And maybe do that, we hope, dozens of times over the lifetime of the mission. It's really, really exciting. And so I'm going to go back a little bit and then head forward to Titan so that we understand why Titan's so important for this Dragonfly mission and go on. But it all started with Cassini. This is a Cassini spacecraft on the left. Look how big it is. This is kind of in the style of Voyager. Just a massive spacecraft that can go out into the solar system, is well instrumented. It can study lots of aspects of a system. And it was launched in 1997 atop this Titan IV rocket. Just before it launched, a big probe was strapped onto the side that actually landed on the surface of Titan. We'll talk about in just a bit. On its way by, it passed by Jupiter, the whole Jupiter system, and got a gravity assist in doing that. This particular picture was not taken by Cassini, it's taken by Juno. And I don't know how many of you have looked carefully at these Juno images, but they are so beautiful. They're like pieces of art to me. Everything you see here is an actual part of the picture. There's nothing emphasized or highlighted or anything like that. The detail here in these clouds and the angular shapes, I think there's a lot of science left to be done here on these beautiful pictures. And oh, and I love this one. Look at this is the Great Red Spot that we're also familiar with. And look at the detail in the Great Red Spot. Look at these clouds trailing behind, like smoke rising up off of a match. Just utter beauty. And what you can see hovering off to the left-hand side here is a tiny little moon. And what you see is the actual color of this moon and the shadow cast onto the red spot over here. This is little tiny Io. Io is about the same size as Earth's moon. And so it's kind of good to remember that these big Galilean satellites of Jupiter are large. They're planets in their own right, in many ways. This is what we would see up in our night sky if we had Io in orbit around the Earth instead of the moon. It would actually even be brighter. The sulfur, yellows, and kind of bluish frosts would all be a lot brighter in our night sky and illuminate our landscape even more. And then you see all kinds of black dots across the surface and maybe even tendril-like flow-looking features that are dark. Those are all lava flows, and they're fairly recent or active because otherwise the sulfur would come and coat them. There's plumes of sulfur being ejected out of the volcanoes and constantly resurfacing Io. And so anything that you see that's black is hot. Right now it's active. There are hundreds of active volcanoes all across Io's surface. And they're there because Io is being tidally massaged by Jupiter. The other satellites that are orbiting exterior to Io, Europa and Ganymede, are all orbiting in a resonance, and that resonance orbit keeps Io's orbit elliptical. So sometimes all of them are on one side and sometimes some are on the other side, and it keeps the orbit elliptical, which means sometimes it's close to Jupiter, other times it's far away. And that difference in distance happens every 40 hours. And it can be as much as 100 meters in stretching the radius of Io, 100 meters difference. So there's a huge amount of friction and then melting of the rock inside. And this tidal energy seems unlimited. So what if one day we run out of our radioactive energy inside of Earth's interior, inside of Venus, inside of Jupiter? The only thing that's left is that the orbit is preserved. And so the tidal energy might continue long past even the death of the sun. And that's a kind of staggering thing to think about, isn't it? So that maybe the interior of Europa, the moon just next to Io, that's got a liquid water ocean, maybe that will stay warm and liquid well past 4 more billion years from now. And so that's also a fun place for us to go and look for evidence of life. Okay, some more zoom ins here of Io. You can see this feature here, this kind of amoeba looking thing. It's about 30 kilometers across, and it's a kind of gently covered lake of lava. There's lots of lakes of lava on Io, and then a lot of them are emitting big tendrils of lava flows that run out across the surface. This big red patch is elemental sulfur that will change to yellow very quickly in the cold environment of Io. And so we visited a place that to me just looked a lot like that landscape, the reds and the greens and the yellows. And it's those colors for similar regions. This is the Afar region of Ethiopia. It's up in the northeast corner, near to Eritrea. And this is a place where the Earth is pulling apart. It's the new arm of where the Red Sea rift used to be that has failed now. And the rifting is happening in the Afar Valley. So we're down a little bit below sea level here, but there hasn't been an opening yet to allow seawater to come rushing in. One day that will happen. And so there are lots of salt deposits because it's a low, flat region, but now it's being kind of buckled up by volcanic activity from underneath because it's being pulled apart. Here my field companion David has got a scarf wrapped around his face because I had left the gas mask in the car. So we're trying to survive at this point. There's lots and lots of sulfur and sulfurous gases. But the landscape is so beautiful. You can see the salt crystals and they're all covered in these reds and yellows, and both from sulfur and also from iron, things we think we would see on Io. Here's the yellows and the reds. Boy, it looks like a handful of popcorn, doesn't it? Yeah, don't eat it. And very delicate salt bubbles that were also beautiful. But the real quarry for us on this expedition was to go up to the top of the Ole volcano. And you can see the gentle slope in the background of a low, broad basalt shield volcano. Very similar to the volcanoes we'd see on Mars, similar, we think, to some volcanism we might see on Io. And we have these also in Hawaii, low shield volcanoes. Notice there's an entire village up here on the edge of the volcano. Where do they run around? Look at these big blocks of basalt everywhere. But they're here. There's sensitive issues with the border, and they also kind of help escort the tourists up the mountain. So it's good business for them. And the tourist industry is starting to really pick up, or did just prior to COVID. Because we're so low, it's very hot. And I said, let's get up that volcano. I want to go. And said, no, we hike at night. It's much cooler then. It's only 95 degrees instead of 105, you know. So we waited for nightfall, and this is what I could see all the way up. It's very windy and just dark and bleak. And a few hours later, we arrived at this amazing site. Still one of the most amazing sights I've ever seen. This is the Ole Lava Lake. Notice it very quickly gets a crust on the surface, but then when it's exposed, it's very bright and hot. I can feel that wave of heat even from 30 meters away. Now this is a different lava lake. This is in Vanuatu, northwest or southwest Pacific. And it's much more violent. Lots more gas, lots more lava. Guide. You can even still see crust forming on these lakes. And so we kind of ask, how much crust is there? Is that important? And because as we look at Io, we're only looking from telescopes. And we're just seeing sort of like a summary of that heat output from the inside of Io. And so we don't have the level of detail that we would on the lava lakes here. And so what we do is bring cameras to help us get the temperature of these surfaces. And so here you can see on the left, this is degrees Celsius, up to 1150 degrees Celsius. And I can get that with the camera and calibrate this correctly. Don't even have to go and get a sample of it, which is really valuable. These places are very hard to access. And sure enough, look at that crust. It's very cool compared to everything else. It's the same temperature as the walls. The crust insulates the lava very well. So you've got to wait for the fountains. And probably it's the fountains that are driving the heat release from the inside of Io. And here's a picture, a cross section of what might happen in Io. You've got these magma chambers, different levels of magma. This is from my thesis a long time ago. I need to publish this one. And then a boiling lake of lava, and you can see a big plume of sulfur being ejected out too. And so we're starting to understand how we can measure this heat release from Io, from orbit, and also even from telescopes on Earth. And we're really hoping for a mission, Io Volcano Observer, IVO, and it's a finalist, one of 4 mission finalists in the Discovery call that NASA just put out. And the selection will happen in July. The review is almost done. So we're really hopeful, but this would orbit Jupiter and it would fly past Io. I'm also on that mission team. And the true question here is there a magma ocean inside of Io? How does Io release all of its heat? And what does that tell us about the early Earth, for example, back when it was much hotter? What environments would the early Earth have? And then how did that lead to life? In some ways, Io can answer that very early Earth question. Okay. Stay tuned. You know, as we were hiking up, I had to tell our guide to slow down a couple times. I was like, you know, this 20-year-old kid or whatever, he was 14 and just marching right up the hill, and I, had to have him slow down. But it's by the light of day. It was wonderful to see him and thank him for all of his hard work. And I really love the cultural aspect of travel. I try to get as involved in that as I can and try to meet as many people as I can. Here, the camels are being used to carry salt up from the salt flats, and this is their job, day in and day out, and the job of the salt miners. This is a very difficult life. And they're really kind to allow us to kind of help, and get our pictures and help lead the camels for just a bit. And of course, that helps with the tourism as well, helps their industry. Okay, well, we continued past Jupiter. This is a little sidetrack as we're heading out past Jupiter with the Cassini spacecraft and finally arrived at Saturn in 2004. And I really love this picture. This is taken from a spacecraft, we know, because Saturn is 10 times as far away from the sun as the Earth. And so the sun is behind Saturn. We have to be farther away from Saturn than that in order to take this picture. You can see the sun illuminating the atmosphere, getting distorted, diffracted by the atmosphere. You can also see that the rings themselves are also doing a tremendous amount of light diffraction. This is emphasized just a little bit in this particular picture. What's also fun is there's a tiny little white dot here near one of the rings. And if we zoom in, it's actually the Earth and the Moon. And there were a number of these opportunities where let's turn back and look at Earth, a very kind of Carl Sagan-like look at our planet Earth and see just how far away and how tiny we are. I think they even mobilized people to wave at the right time so you could get your picture taken by Cassini from Saturn, you know, which is so spectacular and just helps us understand where we are in our solar system and how big this solar system is, and that we're still able to get out to these places with great precision and study them in detail that we just almost can't even imagine. There were beautiful pictures of the rings taken. I feel like I see at least 3 different beats here, different, I guess, wavelengths. And the reason for this is it's a combined result of the spin of the rings themselves. They're orbiting Saturn, and also the tug of gravity from Saturn on the rings. And the combination of those helps to sort of string these out into these long kind of waves throughout the rings. It should be noted too, the rings are blade thin. They are 100,000 kilometers across, but they're just a couple hundred meters high, made of blocks ranging up to the size of a house, most of them smaller than that, individual blocks of ice. And at this stage, we're thinking they're fairly young. This has been the outcome of about the last 5 to 7 years, is that the rings may be as old as the dinosaurs, and that's it. And part of the reason is that they're not very dusty. They should be coated by dust, but they're just laser bright. That ice is not coated by all the dust of the solar system yet, and a number of other kind of dynamical things. So it seems like something crazy happened in the Saturn system just about 100 million years ago. And likely that event, you know, tore apart some object, created the rings, may have created all of these shepherd moons that you can see here that help to create very discrete rings across the large system. There are other objects farther out too. This one is Mimas. It's about 500 kilometers across. And that's no moon, that's space station. This is our Death Star moon. It's just perfectly shaped Herschel crater here. But one thing that stands out here is that it's very heavily cratered. It's an old surface. We think, you know, 4.5 billion years old by way of crater counting. And that's kind of all we can do for a lot of these objects. But the real gem of the system that we intended to visit is Titan. And Titan is really unusual. It's larger than everything except Ganymede. So Ganymede of Jupiter is the largest satellite in the solar system. Titan comes in just behind that. 2,500 kilometers across. It's larger than Mercury and has a big, thick atmosphere that's rich in nitrogen and also rich in organic hazes. Where did the organic hazes come from? It doesn't have to come from life. It can come from dissociation of methane and other molecules in the atmosphere, recombination into long chain carbon and hydrogen molecules. And we think we've observed a number of these in the atmosphere of Titan. So we even knew that from telescopic observations. We knew that from the Voyager missions flying past. And so that was a big target for the Cassini mission. So here's a picture of all of these to compare: Venus and Earth, and then Mars, then Titan, and then Mercury. And the gravity here, because Titan's lithosphere and its mantle is made of water and water ice, okay, and then a core of rock and metal deep down. And so even though it's bigger than the moon, it has a moon-like gravity because of all that water ice. All the objects starting at Jupiter on out have lots of ice. The atmosphere has more pressure and is more dense than Earth's. It's about 1.5 bars, but isn't that interesting? 1.5 bars. If we ever get people out there, think how easy that is to explore. you don't need a pressure suit. You definitely need something to protect everything because it's very cold. It's 90 degrees above absolute zero, but no pressure suit. And that's a game changer because that makes things very difficult in terms of bringing humans along. It's really far away. Who's going to want to make the 10-year journey one way? But still, it would be pretty fascinating. The atmosphere is also Earth-like. It's made of nitrogen, 95% nitrogen, with just 5%, mostly methane and other molecules. Methane outgassed from the interior. So it was accreted at that location. Lots of carbon, lots of hydrogen available there. Okay, the Huygens probe that was on the side of Cassini descended down through the atmosphere and was prepared to splash down in lakes of methane if they happen to be there, or land on a solid surface. And it did land on a solid surface in an old riverbed. I honestly thought when I saw this picture on the right-hand side, oh shoot, somebody put in Mars by accident, or maybe it's the backyard because I was in Tucson. Maybe this is the Southwest and this is by accident. This is a picture of Titan, 10 times as far away from the sun as the Earth. Rounded cobbles you can see in the foreground from being in a river channel. And on the way down, there was lots of evidence of carving by river channels, more well-developed stream channels on Titan than on Mars. And we think this is ongoing. We think there's actually methane rain because it's so cold there that methane is not a gas, it's instead a liquid, and forms clouds and forms rain across the surface of Titan, and may even do that actively today. Okay, well, that's really exciting. Not only was that a dry riverbed near the equator, but when we finally got our look at the polar regions, we found actual lakes and seas of methane. And this is Ligeia mare. This is one sea monster. There is a Kraken mare, and these are, of course, named for mythological sea creatures. And what you can see here, it's dark in color, but that's because we're looking at a radar image. The atmosphere is so thick that we can't see through very well with visible or near-infrared images, instruments. We do have some images of the surface I'll show you in a minute, but mostly the radar can see right to the surface, right through the clouds. And essentially that makes a picture that tells you about the materials. It's not really like an actual picture. So the dark is smooth and the bright is rough. And liquid would be smooth because the signal bounces on the surface and then heads off in the other direction, never returns to the spacecraft. And so it's a dark signature here. We think in general, the liquids would probably be kind of transparent, unless there were things dissolved in the liquids, but sort of a transparent or light color to the seas of methane. And there's a little bit of ethane in there as well. Here is an infrared image of Titan. So this is through windows that could see through that hazy atmosphere down to the surface, and then colored falsely so that we can see different compositions of the landscape here. And I mean, it's a beautiful body. There's a lot going on. All of this orange that you see sitting here in the foreground is one sort of a terrain. Then you can see a sort of purplish, bluish in the upper right corner. That's an entire continental landmass. We think that's lots of water ice is exposed. It's rugged. There are mountains and rivers. That's called Xanadu. And where there's a lot of water ice crust exposed, it's the dark blue and purple. That's around a few randomly spaced impact craters, but there's not many craters here, right? Little round circles. We think maybe 100 across the body. That's fewer than Earth. So there's no heavily cratered terrain on Titan like there is on Mars, on the moon. And then, okay, and then what is all this orange material? The orange is sand dunes. It's sand. It covers maybe 25% of the globe. Encircling the globe at the equator, there are big Sahara-like deserts at the equator, which is where there is evaporation happening the most on Titan. And as we zoom in and look at these with our radar instrument, we can see that these are long and thin. They're about 1 kilometer wide, a couple of kilometers apart, hundreds of kilometers long. And these are also dark to radar because they're smooth. All you would have are little ripples, and the radar wavelength is 2 centimeters. So it's smooth to 2 centimeters. Sand dunes without rivers through them or being cut up by any other process. So we think the dunes are possibly even active All that rainfall has not destroyed the sand dunes. And they are very similar in size and shape and behavior to the large sand dunes in Earth's big deserts. So this is Libya, all across the Sahara Desert in Arabia, Southwest Africa. These big deserts are kind of unimpeded, and the dunes can grow as large as possible underneath our atmospheric constraints. And so what they will do is grow to this size, 1 kilometer wide, a couple kilometers in spacing, maybe about 100 to 150 meters high. And we see the same thing on Titan. And so the atmospheric conditions at the surface of both these bodies are very similar. We already said that the pressure is similar at the surface of Titan to Earth's. And also we think that the atmospheric boundary layer, that layer that interacts with the sand dunes, is about the same thickness as it is on Earth, based on the fact that the dunes are the same. But what are they made of? They are actually made, we think, of organic particles. And this is because as we look at this image again, they're not water ice. We would think, well, isn't it just eroded sort of bedrock? Then they would be bright blue to the infrared spectrometer. But they're not blue, they're brown. And this VIMS brown is consistent with them being made of organics. And so now we have a really interesting place to go is the dune areas of Titan, which is exactly where Dragonfly plans to land, right in the middle of the dunes. You can just grab organics right off the surface. And what do we mean by that? We're still trying to figure this out. Is it like plastic beads? That's organic. Is it like grape nuts? I like grape nuts the best. Only you need to round them. They can't be sharp grape nuts. They have to be rounded grape nuts. It would be the same color and even the same composition. So anyway, we're still trying to understand what it is we're going to see, but it's a big mystery. There's a big leap in our understanding just by going to this place. So we're going to locations like the kinds of sand dunes that we find on Titan. This one is Namibia, Southwest Africa. And now you can kind of see how tall these things are. This took us all day to get up to the top of the sand dune with our instrument, our ground penetrating radar. And what is that going to tell us? I guess I am helping this time, but a lot of times it's the students. They're pushing this thing up the hill, and I'm taking pictures, as we couple this instrument to the ground, it sends a signal down into the subsurface and then returns all this layering. You can see the layering. And what the layering is telling us is there is movement of the sand down the dune long axis. It moves down the dune long axis, and that helps us understand the wind. And so the dunes on Titan can act as wind vanes for us and can tell us, yeah, sure enough, we can line up sand transport, which is generally the wind direction, with the dune long axis. And that can help us with our climate models as well. And then, as we look at the dunes of Titan, that comes back to help us understand this sand dune, because these might be kind of fossil remnant dunes. They might have some activity. You can see there's sand moving around, but really they're big landforms that might have formed during the Pleistocene era when it was very cold and very windy all across Earth. And they could actually be active on Titan and maybe not active on Earth. Isn't that interesting? Okay, well, I've gotten kind of an obsession with wind, and so I'll head out to some other windy landscapes all across Earth. And here's one that I really love. This is in Argentina, the Puno region of Argentina. And what you see that's kind of dominating the foreground are big ripples. These are ripples of gravel. And does the wind get fast enough that it actually moves one piece of gravel from the crest of one ripple to the crest of another? That's incredible. We actually think it's not quite that's happening. We think that the grains are kind of moving along. They're getting impacted by sand and by each other. And they end up shaping themselves into these gravel ripples and ridges. In the background, you can also see some peculiar white towers. And these towers are volcanic ash that's been sculpted by the wind. It's been carved into big, long ridges by the wind. And the wind is using the gravel, it's using sand. Here you can see another set of beautiful gravel ripples on this rock. It's hard enough to walk on. You can pretty easily kind of chisel into it. And we think there's really similar kinds of materials in a region on Mars. And this is called the Medusa Fossa Formation. Medusa, and then Fossa or cracks. And there are whole fields of these kind of wind-carved ridges. And so now if we go visit this area, we have a sense of what the material's like. Oh, it's, it's this soft, you can carve it by the wind, but it's hard enough to hold up your weight. It even helps us think about, could you build some habitats inside of this volcanic ash? And our studies on Earth are helping us prepare for what we might find in that region on Mars. Here's one particular ridge right here. And it's really characteristic of these features. They're called yardangs. And they've got a blunt nose, and then it's kind of tapered downwind. It almost looks like, a ship plowing through the gravel. And you can see the gravel kind of swooping around it because the wind, basically this thing is moving through the wind, isn't it? But it's stationary compared to our feet. And so we're trying our best to study these and understand them better. Here's a corridor between a couple of them. I love being here. It's very otherworldly. There's just nothing that grows here. It's pretty high. It's about 10,000 feet high. So I'm always a little altitude sick, and it just feels kind of neat to be in that environment. We hike through these, and I feel like I'm on Mars when I'm here. I bring students with me. They do great work for me. And here, Jonathan is measuring a dados. It's a finger that points into the wind, and there's a little rock here that's a little bit harder than the volcanic ash. So everything was eroded around that rock, and the protrusion helps us map out the direction of the wind. So same thing, we can figure out what direction the wind was blowing to shape these towers of rock and better understand how they formed. And Dylan is a graduate student who's looking very carefully at rock hardness, and again, trying to relate that to the hardness of rock on Mars. We also have a little model here for what the wind is doing around the yardangs. And again, we can apply that to climate models for Mars. We can also really try to understand just these features on Earth. They're not very well understood because they're kind of rare, they're ephemeral, they're in these difficult deserts. And so we're making a lot of progress on that. We kind of asked ourselves, does it get that windy here? And yeah, sure enough, one day a big windstorm kicked up, and here's the one that I thought, okay, yeah, the wind is active. Here y'all are getting pummeled. I thought, does the sand ever reach head height? Oh yes, the sand does reach head height, reached eye height for sure during that particular storm. Okay, so you can see the action of the wind. You can see there's lots of these pumice holes right here. Pumice is a little bit softer in volcanic rock, and the pumices are getting eaten away by all the sand and the wind. Also brought my drone out. I've got a Mavic 2 Pro, and it's a great way for us to get elevation models put together of the landscape. And then I just like these big sweeping kind of landscape vistas. These are sort of like incipient rock towers. It's like a rock tower landscape, and they're starting to sort of emerge out of that layer. And we're trying to figure out that transition and need to go back. We're hoping this year go back and study these more carefully. Oh, on to the next. Okay. All right, so we're going to leave Titan, and I guess we're leaving Mars for a minute. We're going to head even farther out. I'm sure you all know where this is, what object this one is. And yeah, it's Pluto. If you had asked me, because the Dawn spacecraft arrived at Ceres pretty close to the time when we went to Pluto, or we were kind of planning for those flybys about the same time. If you had asked me what the surface of each of those would have looked like, I probably would have reversed them in my mind and said, oh, Ceres will be really exciting and lots of things going on. And Ceres was interesting, but lots of craters, pretty old surface, right? And then we got to Pluto, and Pluto has got, there are impact craters, and there's even a heavily cratered terrain, but then this giant heart-shaped, it turns out, glacier that is very young. It's so young, there are no impact craters on that, and all kinds of other ices that are cycling around on the surface and creating landscapes that we just haven't even seen on other planets. And it turned out to just be staggeringly interesting. Here's one of my favorite pictures in all of spaceflight. Probably I've already said that. I think I have a couple of them, and I try to show them during these talks. But this one, I mean, it just doesn't look like you're on Earth. and looking out, you're looking at some mountains here, and there's a big glacier that's flowing, and then there's a hazy atmosphere in the distance. This is planet Earth, surely. It is not, it's Pluto. And the mountains are made of water ice, which is more rigid at this temperature, 30 degrees above absolute zero. Rigid water ice blocks, and then the nitrogen can't even be the atmosphere anymore. It is collapsed onto the surface as a glacier and is flowing. It's got a texture kind of like toothpaste at these 30 Kelvin temperatures. And then there is a little bit of an atmosphere of nitrogen and some carbon dioxide up there, forming an atmosphere with some hazes, again, organic hazes. As we head out into the outer solar system, the theme is water, ice, and organics. And so now we're turning our attention to these locations because, yeah, we've got all those ingredients, and maybe we just were looking too hot. We were looking at Earth. And actually, if you lived on somewhere like Pluto, you would say, gosh, how do you live on Earth? You have a magma ocean on your surface, because our oceans, you know, it should be water ice if we're at Pluto. And so they might say, how could you possibly have life there on Earth? And it's all a matter of kind of rates of process and rates and energy needs and things like that. We were able to, just a friend of mine and I were looking together on Facebook one day. He was in the UK and I was here, and I said, gosh, look at those beautiful dunes on the glacier as we kind of zoom into that nitrogen glacier. And he said, what about those dunes? And so we contacted Alan Stern, the PI of the mission, and said, hey, is anybody working on the sand dunes? We could help. And he said, no, there's no sand dunes. And so we kind of put some ideas together and showed it to the team and said, we really think these are sand dunes. And they were really gracious. And they said, gosh, that was a good one. We should have seen those, but yeah, sure. Write your paper. And we put a paper out about sand dunes. But I mean, the problem is, I thought we said there wasn't much of an atmosphere. So you need to have wind for sand dunes. We found just enough wind to be able to carry very small particles. And then also you need to have sand. And what could the sand be? I guess I'll take a little break here quickly and just say, well, how did we know these are sand dunes? And it's because we've been looking at sand dunes on Earth. Both he and I, we've been visiting sand dunes. This is more like a little pocket dune field. This is in Death Valley, California. I recommend anybody to go to Death Valley. It's really spectacular. And these just sort of pile up in these little collections. They look a lot like the same kind of patterns that I saw on Pluto. Here's a student here collecting some sand. And so, we were prepared to look for those, and people saying, well, there's no wind, or what's the sand? I always say, look, I'm relying on the shapes. The shapes tell me these are dunes. So if any of you want to find the wind and the sand, then that's okay. But I see dunes. And sure enough, an astronomer, Will Grundy, came through for us and said, hey, I've got this, infrared instrument that has taken a picture of the surface, and it's found a tremendous amount of methane ice in the region where your dunes are. And so we think that this methane ice is formed up into snowpack up in the mountains, and then gets blown down by the wind, these cold katabatic polar winds that blow downward and carry with it all that ice. And so basically it's methane ice sand that are the sand dunes on Pluto. So it just gets crazier and crazier, right? Well, it kind of reminded me that it wasn't so crazy because I have been to Antarctica. And in Antarctica, the snow sinters together and makes a sand and becomes just like a dune. So here are some big dunes forming behind our tents. This big pile wasn't there before. The wind carried it there and blew it into a big pile of snow sand, basically. And here's another kind of crazy windstorm. And you can see the ripples, the big ripples in the snow, the ice sand that is forming here. We can't go out on days like this because it's just a little too crazy. But normally, once the wind dies down, we go out and we look for meteorites out in the field. And this to me is really the kind of perfect combination of planet Earth and outer space, because the two are together. First, you have to get to the very far reaches of planet Earth, the tiny corner where you have to work hard to survive. And then once you can reach that place, space sends you material. And you can go and recover meteorites from all across the solar system. They land evenly on planet Earth, but the glaciers of Antarctica carry them to certain locations, and we can collect a lot of them there, usually hundreds every season. And here's me spending a little moment with the meteorite before I call everybody over. And we carefully pick it up with tongs and bag it. And they get sent to Johnson Space Center and also to the Smithsonian for analysis. And then anyone can request to study them. But we found meteorites from the moon and from Mars, free samples from these bodies. And it's a really special program. So it's called the Antarctic Search for Meteorites program, where you can Google ANSMET and follow a blog about their meteorite recovery efforts. I believe they are casualty to COVID again this year and will not be going down. They're doing kind of a bare bones season, I'm pretty sure, so they may not be down this year, but next year they'll be back. Here we all are lined up on snowmobiles and waiting to drive off into the distance and look for these little tiny black dots on the surface. And it's one of my favorite things that I get to do here on Earth. Okay, so just to finish up, it's a kind of riot of a lot of information, but let's go back to Dragonfly for a minute and talk about what it's going to do. It's going to fly over and land in the sand dunes. It will see a variety of landscapes. And so here are all the different kind of cameras that are on board. There will be panoramic cameras. They can both do landscapes, and they can also kind of look out over the dunes. And here we're looking at Bagnall Dunes on Mars as an example. Here's a forward looking, and then downward looking, we're getting more detailed. And finally, we can even have a picture of sand, a little kind of handful of sand. And you can learn a lot about a region just by picking up the sand. It's flowed there through rivers, it's been blown by dunes. And in this handful of sand in the bottom here, this is Bagnall Dunes again on Mars. What we can see is, okay, they're mainly basalt grains, and there's a little bit of sort of evaporites in there, which is interesting, clays, things that might have come from regions where water collected on Mars. And so having all that together in the sand dunes and sand grains is really valuable. We want to do the same thing on Titan. I'll move on to the next. So here we are landing in the dunes. We also have on board a mass spectrometer. As we mentioned before, a drill. We'll pull these things up into the interior, into the body. And really what we're curious about is how complex are these hydrocarbons, these organics. We'll be able to tell, here's the molecular weight, and here we'll be able to see peaks at certain molecular weights that would tell us something organized that particular molecule, or that molecule is comfortable at this at these conditions on Titan's surface. And as we study those particular molecules, we can start to say, hey, you know, maybe life preferred this molecule, or maybe chemistry progressed to a point where life could start on somewhere like Titan. And so we're looking at just how far this prebiotic chemistry progressed. And we can even see things like the chirality of the molecules. Remember, a certain spin to these organic molecules, just a 50-50 spin might indicate nothing special is going on. But if you have everything as a right-hand spin or a left-hand spin, like on Earth, then life has preferred that left-hand spin and uses only that. And so there are a number of tests we can do to really look for this evidence. Why should it be on Titan? We've already mentioned that there's lots of organics on the surface, in the sand dunes, in the rivers and lakes of methane, in the atmosphere. And then the crust itself is made of water ice, just like the other icy objects. So if there's an impact event that could melt water, melt the ice and make water. So we're going to fly to where there's an impact crater and study that region. Maybe there's also been cryovolcanoes, volcanoes from the interior, that bring that water up to the surface. So only on Titan can we see all of these things happening on the surface. On Europa, we think we've got to go down into the oceans. On Mars, we think we've got to kind of go below the surface and get down into the subsurface. And so really Titan offers this next step to help us answer those questions. What made it planet or moon habitable? What are the chemical processes that led to the development of life? We still don't know what started life even on Earth. And has this happened somewhere else in our solar system? So this is being built right now. This is at Johns Hopkins University Applied Physics Laboratory. You can just Google Dragonfly Titan and that webpage will come up. Its current launch is now 2027. But just this week, we found out we get to go on a, do we know this? Yes, I think it was tweeted. I always have to check that. We get to go on a heavy launch vehicle. We don't know which one yet, but that will cut off the time it takes for us to get there significantly. So we should be able to arrive on the surface of Titan by 2034. And that sounds like far away, but I'm very excited now. All of a sudden it's 2034. That's within reach, right? And I will get my handful of sand. This is what I do everywhere I go. I pick up a handful of sand, try to find out what is happening. And this was really special. This is in Kauai. I heard about a glass sand beach. How can you have glass sand? And I picked it up, and sure enough, yeah, it's all glass particles. All you have to do is march around the corner to find the landfill with all the glass bottles that's creating that sand. And again, it's a little kind of breadcrumb trail. You pick up the sand, and then you can kind of follow your way back to where it all started. And that's exactly what we want to do on Titan. Okay, that is all I have. If anybody has questions, I'm happy to answer them.
Thank you very much.
Thank you.
I have a few questions. What is the vehicle powered by? Is it going to be nuclear powered?
Yes, it's an RTG, and I always radioisotope thermoelectric generator. I think nuclear's got to be in there, but essentially it's a plutonium battery charger, right? So there's decay of the plutonium that creates heat, and the heat charges up a battery. And so, yeah, that's vital for this location in the solar system. It's just too far away for solar panels. Plus, we're down through the atmosphere of Titan. The good thing about the radioactive batteries is we think they should last, at least 3 years. So that's really good length of time. You can actually kind of see it in the back. Do you see that big sort of round thing in the back? That's the battery.
Yeah. And the vehicle, how in the world is it going to communicate back to us?
Can you see this tiny little round thing right here? It has to be a direct to Earth communicator. And so, we don't have enough money under this cost cap to have an orbiter around Titan, which would be really helpful. But instead it has to communicate direct to Earth, which means it's got to be near the equator so we can see Earth. And then also the data that come back, it's almost unfortunate that we had this spectacular landing of Perseverance rover and the video of the landing. We can't have video for this, poor little very distant spacecraft. It's going to be a very different way of doing outreach. People have to be patient with the fact that data's got to trickle down from far away in the outer solar system.
So the radio transmitters have to be not that powerful. So you're going to require deep sky network? Yeah,
we have to use deep space network. It's the 370-meter radio telescopes that are scattered across Earth.
Wow.
I believe we might also be able to use the 35-meter, if I remember right. So that's good news too. But it's pretty amazing that we can even communicate with this one spacecraft as it is. So we're lucky that worked.
Insane. When you were, I'm sorry to take all the questions. I wrote them down. That's what we're going well. When you were saying that these orbital instruments take radar of the surface, how powerful is that radar? Does it penetrate or just topical?
Yeah, so the radars tend to be pretty big power hogs. You're right. So you're sending a signal down to the surface and it returns. We did the same thing at Venus. So any pictures you've seen of Venus's surface are radar pictures because that atmosphere is also very thick. And then there are some neat radar images of Earth. I really should put some of those in because there's detail that you can see that's a little different from what we see in regular pictures. And all the sand dunes in the Sahara are dark in color, just like the radar pictures of Titan's dunes. So on Titan, because we've got a water ice bedrock, we even think there's sort of maybe organic rocks sitting on the surface. The radar can penetrate through that material, maybe even up to a couple of meters, and can possibly even penetrate into the lake materials as well. So some of those lake images we saw you might be able to see below the level of the methane that's filled it. That creates a lot of challenges because it's hard for us to interpret, why is this so bright just because it's fractured in the subsurface? And is this so smooth just because of, it's filled with dust perhaps? So there are still some interpretation challenges with radar.
All right, thank you very much.
Is there any concern about the ability of Dragonfly to fly in? I mean, with all the discussion of dunes, I'm just concerned about whether it's able to fly all the time or whether some of the components on the Dragonfly would be eroded.
Yeah, by moving sand.
Yes.
Yeah. So for one thing, we think the rates of processes are very slow on Titan. And so even though, wind has got to blow and it's got to move the sand around, it's possible that even is kind of seasonal or ephemeral just during storms. And even the storms are not sort of the big convective thunderstorms like we have on Earth. They're kind of more gentle stormy storms. We may only get up to 10 meters a second. That's still decent, but it's well within the ability of this quadcopter to be able to handle that. And so we actually are predicting that we're going to have to generate our own wind with the propellers so we can watch the sand saltate around and move around. It may not even be that we get any wind. And part of the reason we say that is we watched the lakes very carefully, and we didn't see wind ruffling the surface of the lakes. We didn't see a lot happening. There was one instance of a possible dust storm that was observed by VIMS. Kind of a cloud hovering up there that wasn't an atmospheric cloud. It wasn't on the surface. It took a while to work around. They said, oh, this could be dust. So that was kind of exciting to see that. Yeah, I mean, there are a lot of things that we'll have to just prepare for and just say, we want to prepare for this scenario, this, and make it very robust. So if we see any of those things, the aircraft will be okay.
No dust devils like on Mars?
No, we don't think so. Yeah, Mars has got a little more energy because it's closer to the sun. Oh. And not only that, I guess those dust devils are still, even though they look kind of crazy, they still just sort of come by and clean the solar panels off, and that's sort of it, So they don't have a lot of energy to do a lot of damage or flip a spacecraft over or anything like that. And there'd be even less energy on Titan for that.
Wow.
Would Dragonfly have to be stationary to communicate, or can you communicate while the thing is moving?
I believe it needs to be on the ground to communicate. So we need to have the sequence pre-planned, and it's a really kind of interesting, kind of a clever idea. The first is, as it's landing for the first time, it will overfly a future spot that might be kind of close and take a lot of data for that, and then come over here, and it does have to sort of land at its first spot a little bit blind. So there's landing radar, there are other kinds of things. We can't fly it with a joystick because it's an 1.5 hour time delay. So it's got to have some autonomy and be able to land in that first place safely. But then once the data for the new spot is on the ground, we can very carefully say, okay, here's exactly where we want you to land. Before it lands at the second spot, it will overfly the third spot and accumulate data there and then come back. So it's a leapfrog technique that will help us to very safely go to all the places. So the real nail biter is that very first landing, kind of like with any of our NASA spacecraft, right?
What's the expected life of Dragonfly?
We have a nominal life, I believe of 90 days, and we can accomplish a number of really important 90 Earth days, accomplish a lot of tasks there. We're required to do one leap to a new spot, but we're hopeful. We're designing the mission for 3 years and dozens of landing sites. So far, the mission design that NASA has done has been good. I mean, remember Spirit and Opportunity lasted 14 years or Opportunity at least, instead of its original 60-day lifetime. So we feel we can engineer it out quite a ways.
Now, Spirit and Opportunity had to go through seasons.
Yeah.
It is where it was shut down. Will that happen here? Are there seasons that we need to be concerned?
There are seasons on Titan, but it turns out that each season is about 7 Earth years long. And so I think we'll be there in kind of mid-southern summer. And we'll kind of be there for mid-southern summer. But that's interesting because we only got northern summer with Cassini. So now we get to see southern summer with Dragonfly, and that will be different and valuable for us to see that difference.
That's great.
I have some geology questions.
Sure.
Oh, okay. With regard to the dune morphology, periods, amplitudes, whatever, can you use it to tell you anything about the grain size distribution that you're dealing with?
To some degree, yes. Most dunes, regardless of the type, have a fairly, first of all, a fairly even distribution of particles within the dune itself, and then also all other dunes have that same sort of distribution of particles. So dunes just like to be formed at sand sized. And you probably have noticed that as you go to the beach, you pick it up. In general, the sand is kind of like one size. You'll find regions where it's more coarse than others, and it could be kind of faster flow of channels out to the beach, or in a river on the sides, things like that. And so that's a beach example. The dunes are even more sort of uniform in their particle size. And that's because you need to have a size that's big enough that it won't just get sort of tossed up as dust. So all the dust gets tossed up first by the wind. And then not so big that the wind can't move it. So it's in between. And so the wind will pick it up enough to just sort of impact another sand grain, which will impact another and another. So it starts out with the saltation and then impact movement downwind. And winds on the earth are kind of able to just pick up that same sand size all the time. What we should be able to find out, though, is that typically the crests of dunes have a finer grain size, and then the flanks have coarser grain size. I'm really eager to see that difference on Titan, because to me that heralds activity. The one thing we can't do, though, is land up on the crest of a dune. The engineers would just lose their minds if we tried to do something like that. So we've got to stay on a very gentle sort of like 10-degree slope, and then, go up as close as we can. We can, kind of hop over to the edge, which I would like to do, and a lot of dune scientists, who are on the team, and get right to the edge and see what that grain distribution is like on the margin of the dune. Thanks.
Sounds like something that you could make use of ground penetrating radar on one of your airborne rovers here.
I agree.
You get close enough to it, you could actually start looking at climbing ripples and other fun stuff below the surface.
Yeah,
I guess that would be kind of expensive, though.
Yeah, we couldn't put the ground penetrating radar on. Definitely that was a consideration, but again, for just like power, it didn't work. So we're going to have to rely a lot on imaging, and you can do a lot with imaging. You can get a sense of like the ripple distribution and how sharp is that crest line, which direction is it, when did the wind shape it last, and I think even we may get a good sense of size distribution even from the air of particles. I'm hoping. For sure, cobbles from rivers versus the sand from the dunes. And I'm excited to see the differences in those landscapes. I really think we're going to see a very Earth-like landscape, only remembering that it's formed in different materials, just like on Pluto.
Do you see different kinds of dune types, I guess, so barcans, other kinds of dunes, or would that tell you anything?
It would definitely help us if we could see that. One thing is that our resolution is on Cassini was just kind of barely good enough to be able to see these big linear dunes. We do think in most regions, we don't see that there's just like, a big blob of sand trailing off. Sometimes we do see that, but it's not really abundant. So where we do see a blob of sand trailing off, we think, I bet that's a bunch of barkans trailing off the edge, right? Because we see that on the Earth. And that helps to tell us the winds have changed a little bit. I feel like the fact that everything is very comfortably shepherded into these linear dunes means that they're in equilibrium. And when I look at dunes in Arabia, I see these big, pretty linears and then lots of barkans shed off toward the south because they're not in equilibrium now with the current winds. And so the Arabian dunes are telling me climate change, shift in winds, and I just don't see the evidence of that on Titan.
What about water sedimentary structures, subaqueous dunes, anti-dunes? sand waves? Do you see anything that would be indicative of? I realize that the wind would have reformed anything once water is gone.
Right.
Maybe this is a question for Titan, where you have a fluid body. I guess you can't really see anything below the surface of the lakes.
No, but and one difficult thing for us is that the lakes are all at the poles, and we can't go near the poles because we can't communicate back with Earth. I know it's really hard. But I'm pretty confident that we're going to run into some liquid methane bodies, like maybe swamps. I've seen evidence of things that to me look like swamps near the equator, and maybe even some active river channels. So, but then also, as you say, dry river channels will still tell us a lot because the sedimentary deposits are sitting there, not obscured by the liquid in place of it. So we do see lots of dry channels all across the equator. And definitely, I think we'll be able to see a lot of those same sedimentary structures. That would be really good.
Do you expect to encounter methane rain?
We hope so. I think that would be really neat. Can we see it? Let's think. I guess you just would have to rely on the imagers. We actually do have a seismometer on board. It's a geophone, so it's a very simple seismometer from the Japanese Space Agency. And that will be deployed on the ground, when we're sitting, and listen for Titan quakes. That would be really valuable. But perhaps if it's sensitive enough and there's a big enough rainstorm, it might pick up. And that'd be neat to hear kind of a rainstorm going on. We did see some evidence with Cassini of a region, it was pretty large, just south of the equator, that changed in color in a broad area in the visible and near infrared images. And then after, maybe a few weeks, it changed in color again back to what it was. The best explanation is it just got poured on by a big rainstorm and then it evaporated away and left behind the original landscape. So it's not impossible.
Well, it sounds like it'll take the paint off of it.
Yeah, that's true.
The opposite, is it possible there'd be glaze? That you'd have a buildup of methane ice on your instruments until it evaporates?
Right, I know, yeah. Luckily, it's not quite cold enough for methane ice on, and especially the equatorial regions. Well, I mean, all of Titan, I should say. All of Titan is a fairly, just within a degree or two of itself because of the thick atmosphere. So 90 Kelvin, and we need to get to 70 for methane ice. That's, thank goodness. And we don't have to worry about de-icing. Yeah.
Why is it not possible to communicate from the poles?
Because Titan so it's orbiting Saturn. Saturn has a tilt of about 24 degrees. So Titan also has about a 24-degree tilt. If we were up near the poles, you got to kind of communicate way over here with Earth, and you're up at the pole. You could be at this south pole, but even then, it's just really low trying to reach the Earth with that. So we don't want to go past too high of a latitude.
So Saturn's in the way.
No, it's mainly, I know that could be, it's mainly that tilt, I think, is just a little too much. You're just like looking way low on the horizon, and I guess maybe even through the atmosphere, that starts to be a problem.
Okay, thank you.
Thanks.
How are you going to gauge the surface as far as whether it's too soft to land on or anything? Because it's like a last-minute decision. There's quite a time lag there.
I agree. It's kind of, it is a challenge, and we don't understand the nature of the organic materials that are in the atmosphere. But in looking at the surface and just the fact that these dune regions are so similar to those on Earth, that tells me that it's got to be loose sand. It can't just be sort of like gushy sand. It's got to be loose so that it can be picked up and blown by the wind, or else they wouldn't look like dunes. They'd look like something else. And then the region between the dunes looks like it's pretty clear of sand, just like places in Egypt and other areas where the sand's only sorted into the dunes, and then the in-between areas don't have any sand. So we picture it just being a pretty solid, hard kind of intradune landing area. But I think we'll see a lot of variety. And I have some plans in my mind to pitch to some of the mission leaders that, let's go look at some of these interdune areas placed between the dunes all across Earth and assemble a good database.
I noticed that one of your pictures showed dunes with dunes on top of them. That is, it looked like you had big dunes with small dunes superimposed on them. I'm not sure which picture that was, or I'm not even sure at this point whether it was on someplace other than Earth, but you did have one picture that showed dunes. Yeah, that's it right there. So you have dunes on top of dunes here.
Yeah, this is actually a really unique aspect of Mars. Mars has got very curious atmospheric conditions such that there's a kind of intermediate dune. Because normally we just see dunes and then ripples for us, right, on the Earth.
Yeah.
Mars has this intermediate form, and we're not completely sure what to call it. And there's a lot of discussion in the literature about it right now. They're called fluid drag ripples. And so they're a little bit akin to what's happening like under a river channel or maybe on the coastline. As you're out far enough, you're snorkeling, you can see these big kind of ripply things being formed by the surf. Why should a low density atmosphere produce something that forms also in a high density surf, liquid? It's just a kind of equating the fluid dynamics in both places, and it ends up working out that way for Mars. I think we expect a much more Earth-like condition on Titan, but of course anything can happen, right?
Well, there's various flow regimes that sort of repeat themselves at progressively higher flows. It's almost, they have a lower, what's it called? Oh, I can't remember. I have to think back to sedimentology. There's a lower flow regime, flatbed, and then there's an upper flow regime, and then there's a series of dunes, anti-dunes, I forget, chutes and pools.
That's good. Your sedimentology is better than mine, probably.
but the point is that there are different you have multiple fluids here, and they have different properties, and similitude allows them to form certain structures at different velocities and grain sizes and so forth. And so it's just that if you have something superimposed on something else, like ripples superimposed on dunes, there's got to be either the old dunes are relict, and you have the smaller dunes, just because of a different flow regime that's come in, or there's some really complicated process where they're both forming at the same time, or maybe there's the big dunes form during storms and the smaller dunes are there's got to be some way that you could pick a certain area and mark it out, and then do kind of like a baseline or just as a case study and just watch it over time to see what happens. But you need the baseline and I guess that costs a lot of money though.
No, we've done similar things on Earth, just as you describe, and sure enough, what you find is that the ripples are the most dynamic and the easiest to change. And so often the larger dune form will take longer to kind of to erase or to change over time. It's got more inertia. And so you might be able to march ripples right over the big dune. They might be able to march the ripples over bigger ripples. We even see that where small ripples overtake big ripples. And so, so we have done a bit of that already, kind of looking at what's the difference? Why is this working this way? And also we have studied some regions like in Mauritania and other places where there's the big, large dunes, and there's a bunch of little ones on top of them. And that tells us that something else happened after the big dune, different regime, and those smaller ones are younger and more recent.
I see.
Nice, thank you.
Hi, this is Mike, and I'm here with Mikel and Andrea. And they had a question about Io, whether Io has an atmosphere and whether or not the volcanoes are helping build an atmosphere for Io.
And if there is an atmosphere, if smoke's gonna, if it gets mixed up with smoke, what's gonna happen?
Right, very good question. And in fact, you're absolutely right that the volcanoes themselves make a little bit of an atmosphere at Io. It's very thin and local to the volcanoes, kind of transient. And what happens on Io though, because there's no other kind of thick atmosphere like Earth, you don't see like billowing smoke coming up like we do on Earth. That's from convection that happens in the Earth's atmosphere. So instead it kind of ejects ballistically. It comes out like this and drops back down like an umbrella, right back down to the surface. And we see lots of umbrella shaped volcanic deposits all across Io, sitting up above the edge of Io. When we catch the sunlight behind it, we can see those things happening. And mostly it's sulfur dioxide, a little bit of sodium and oxygen in the atmosphere. But that's an important thing. We even see the atmosphere can kind of collapse when it gets into darkness. The sun is not helping to keep it up, and then it expands again, and then it collapses again. So that would be a really exciting thing to look at more carefully with IVO. Good question, thank you.
Okay, if just to let anybody that's listening on YouTube, if you do have any questions, you can put it into the chat and we'll ask it here. And if anybody else that's participating in the Zoom meeting, you can unmute yourself and ask your question if you don't realize that. So we'll give that like a minute. This current questions that were asked on YouTube, you have already answered them as the talk has gone on.
Good.
This has been great, Jani. It was fantastic. Thank you.
Good. I know it's just a hodgepodge of a lot of things, not a ton of depth in each.
Oh, no, it's great. Plus, very little has been mentioned of the dragonfly. We're all aware of it, but there really isn't much out there.
Yeah, it's interesting because NASA definitely does things in a certain way. And so there's been a lot of attention, rightly so, on Mars because of all these great things happening. And that has been great for NASA, all of that attention. And often we'll be lucky if we get it for a planet for a while and then it goes back to humans, right? And so there's always a lot of attention on the human space flight. I think a whole bunch of astronauts just convened together in the International Space Station this week.
Yes.
And that almost eclipsed the helicopter on Mars, right? So, so we're lucky when we can get anything said about, and Dragonfly so far out still, I think that's part of it. It's just, but they're developing it, they're building it, they're doing all kinds of things, or not building, designing it right now. So, yeah.
And it was interesting just to hear a bit more about the stuff to study Titan a bit more, because again, having something different than Mars, and the details actually we've had on understanding stuff on Titan.
Good.
All right. Well, I think we're good for nobody's posted anything on YouTube for any questions. So if everybody's questions have been answered here, I think we can call it a wrap.
I just wanted to say thank you for doing this. Very informative. Also, just realized I saw your talk on your trip to Antarctica that was posted through Rutgers, and that was fascinating as well. So thanks twice.
Oh, good. I'm so glad. Yeah. I was happy to put just a couple little teasers in there about Antarctica this time.
There is a question that just popped up on YouTube.
Oh.
Yeah.
It's from Glenn Salka. If there is microscopic life on Enceladus, will sampling the plumes detect it?
Enceladus is another really great place. I'm sorry I skipped over that. It's another moon of Saturn, and is about the same size as Mimas that we showed, the Death Star moon, but it's got a really young surface, very young fractures in the icy surface. And one of the major discoveries of Cassini is these geysers or volcanoes, really, of water being ejected out of the South Pole and into space from Enceladus. As a big surprise because it's so small, it should be cold and dead like Mimas, but it's active. And so that's very exciting because the water's in contact with rock in the interior. So there are nutrients, there's water, there's energy that's ejecting those things. And as you said, it's already being sent out to space. We don't need to go down and get it like we would need to at Europa, potentially even having to drill through the ice at Europa eventually to get to the liquid water, right? So the water is being delivered to us. The biggest challenge right now for Europa or an Enceladus mission is that when you get to that location, you're going very fast. You're going as fast as 17 kilometers a second. And if you open up your capsule and grab big complex molecules, they will shatter instantly and break apart. And so you'll be able to tell, well, there's this much carbon, there's this much hydrogen, but what was the molecule that we started with? And we have not solved this problem yet. It's a very big problem. I think we'll figure it out at some point, but that's the challenge right now for an Enceladus mission.
And when you figure it out, maybe you'll be the author of the Field Guide to the Fish of Enceladus.
That's right. I think that's got as good a chance as anywhere to have something. It's really amazing. Yeah. Good.
Okay, no more questions on YouTube.
Okay.
Okay, so I'm going to end the stream. All the members can stay on the Zoom meeting. So.
Wonderful. And I've got to run too, but I really enjoyed being here. It was so fun. It's just so great to talk to everyone.
Thank you very, very much.
Yeah, thank you.